Substances can exist in the form of solids, liquids, or gases. A system can be made up of one, two, or all three phases of a pure substance, depending on the conditions of temperature and pressure. In this lesson, you will get to investigate the equilibrium between the phases of a system. You will also study the relationship between these phases using the phase diagrams of water and carbon dioxide as examples. Click on Activity 1 to begin your investigation. Here is a quick summary of the processes occurring when a solid is heated. Look at the way the particles are moving while keeping an eye on the temperature gauge on the right. How are the particles arranged in a solid? Answer: the particles are in contact and in fixed positions in a regular arrangement or lattice. How do they move? Answer: the particles vibrate about their fixed positions with increasing energy as the temperature rises. What happens to the particles when the substance melts? Answer: the particles have absorbed enough energy to break away from their fixed positions. What happens to the temperature while the substance is melting? Answer: the temperature remains constant. What is this temperature called? Answer: the melting point of the solid. As the liquid heats up, the particles gain energy until they have enough energy to break away from each other and form bubbles of vapor in the liquid. What is this process called? Answer: boiling. Again, the temperature stays constant until all the liquid has gone. What is this temperature known as? Answer: the boiling point of the liquid. What other external factor might affect this temperature? Answer: the atmospheric pressure. How would you describe a gas in terms of movement and arrangement of the particles? Answer: gas particles are far apart, moving randomly with higher energy compared to the liquid and solid particles. In an open system, the particles can escape into the atmosphere. When a liquid is placed in an empty, sealed container at a fixed temperature, no matter can enter or leave the system. This is called a closed system. Look at the sealed container of liquid. Why is the vapor pressure low before the liquid is placed in the container? Answer: because there are no particles present as a vapor. Why does the pressure start rising? Answer: there are more vapor particles colliding with the walls of the container. After a while, what do you notice about the pressure in the container? Answer: the pressure remains constant. What does this tell you about the particles in the vapor? Answer: the number of particles is constant. Explain your answer. Answer: the system has reached equilibrium. It is a dynamic equilibrium because particles are moving to and fro from liquid to vapor at the same rate. This equilibrium system consists of two different parts, the liquid and the vapor. Both are homogeneous. That is to say, each appears the same throughout. Although they consist of the same particles, the two parts differ in the way the particles are arranged and the way they are moving. Such parts of a system, separated by a distinct boundary, are called phases. This is therefore a two-phase system. Phases do not have to be pure substances. A solution of sugar in water is a single liquid phase. A mixture of oil and water, on the other hand, is a two-phase system. Why do you think mixtures of gases such as air are single-phase systems? Answer: gas mixtures are single-phase systems because all gases mix to form a homogeneous system. What three phases are present at the edge of an iceberg floating in the sea? Answer: a solid phase, ice; a liquid phase, seawater; a vapor phase, air. On the previous page, you saw that in a closed system at a given temperature, a liquid reaches an equilibrium with its vapor. The pressure at equilibrium is called the vapor pressure. It changes with temperature. These changes can be represented on a vapor pressure curve. Click and hold the cursor as you move it about over the center of the blue area, without letting the particle diagram touch the curve. What is present in the system in this area? Answer: the liquid state only. Do the same in the white area. What is present in the system now? Answer: the vapor state only. Now place the cursor on the curve. Click and hold down while tracking up and down the curve. What is present in the system at these pressures and temperatures? Answer: liquid and vapor in equilibrium. Points on the curve represent the equilibrium between liquid and vapor. It gives the pressure and temperature conditions for liquid and vapor to coexist at equilibrium. What happens to the vapor pressure as temperature increases? Answer: vapor pressure increases. This diagram shows the liquid vapor curve for water. Note that it is not to scale. Place the cursor on the curve at a vapor pressure of 101 kilopascals, 1 atmosphere. At what temperature does water exert this vapor pressure? Answer: 100 degrees Celsius. Water at 101 kilopascals will form bubbles of vapor at 100 degrees Celsius. This is the temperature at which the vapor pressure equals the atmospheric pressure, 1 atmosphere, and is taken as the normal boiling point of water. The temperature will remain constant until all the water is turned into vapor. But what happens at lower or higher pressures? Move the cursor up the curve to a higher pressure value. What must happen to the temperature of the water to reach this higher vapor pressure? Answer: it must be increased. Raising the pressure on a liquid, therefore, raises the temperature at which it will be able to boil. Conversely, lowering the pressure on a liquid lowers its boiling point. The vapor pressure curve is known as the boiling point curve. Now let's investigate the effect of changing the temperature of a liquid-vapor system at a fixed pressure. Place the cursor on the curve at 100 kilopascals and click on the point to see the particles. How many phases of water are present? Answer: 2. Now, keeping the pressure constant, move the cursor to a lower temperature near the middle of the scale. Click on the point to see the particles. What is present in the system at this temperature and pressure? Answer: water in the liquid phase only. Repeat the exercise, this time moving to a temperature at about 130 degrees Celsius. What is present in the system at this temperature and pressure? Answer: water in the vapor phase only. This type of diagram therefore provides a useful way of investigating or predicting phase changes of a substance as temperature or pressure is changed. The areas in the phase diagram represent single phases. The curve itself represents conditions of temperature and pressure where the two phases exist together at equilibrium. Summary: a closed system is one in which there is no loss or gain of materials to or from the surroundings. Equilibrium is the state at which the properties of a system do not change with time. A phase is any part of a system which is homogeneous and separated from other parts of the system by a distinct boundary. The liquid-vapor curve gives the vapor, pressure and temperature conditions for the liquid and vapor phases to coexist at equilibrium.